Okay, final video of the lecture, guys. So what we're going to talk about here is how E2 reactions, so specifically bimolecular elimination reactions, are affected by the steric bulk of the electrophile. And so we see that they have the opposite selectivity that we see for SN2 reactions. Specifically, tertiary alkyl halides react faster than secondary alkyl halides. Would help if I could write correctly. And that reacts faster than a primary alkyl halide. And so the big difference here is that unlike SN2 reactions where we see a dramatic effect on the substitution reaction on the substitution of the electrophile on the reaction rate, to the point where terp-butyl X groups will not react at all in an SN2, we see a moderate effect here in that, yeah, tertiary alkyl X are going to work faster, but primary alkyl X, yeah, they're going to work too. So it's not a big deal there. You'll notice also I have not included methyl X, where we did see that on SN2. Just remember, you need 2 carbons to make a double bond. I made that mistake the first time when I wrote these notes down. So can't make a double bond with methyl iodide in that respect. So why we see the selectivity can be explained with a reaction coordinate diagram. So if you need a few seconds to copy down the notes here, feel free to pause the video. But when you're ready, go ahead, resume, and we'll talk about the energetics. Okay, welcome back. So what we've got here is we've got a reaction coordinate diagram for an E2 elimination starting with a primary alkyl X. So I've got ethyl bromide here with some sort of base, B-. I've been relatively generic in this case, so we don't have to really worry about this. So this is going to go up and over a hump and then give us our final product here. Okay, so let's think about how this would differ for a tertiary alkyl halide. So what I've got here is we can envision this is about at the same level. Turns out if you overlap them perfectly, you can't see. So just imagine that they're about the same. I've got terp-butyl bromide, and this is going to go up and over a hump and form a product. In reality, our terp-butyl bromide will form a slightly more stable alkene, so we'll make that a little lower. But the cool thing about this is, just draw the product, plus protonated base, plus bromide minus. The nifty thing about this is that our activation energy, so the distance and energy we have to climb in order to get to the transition state, is smaller in the case of the terp-butyl bromide than it is with the ethyl bromide. So the reason for this actually has to deal with the structure of the transition state. So let's actually think about what these guys look like. So the transition state for our ethyl bromide species is going to have bonds partially broken and partially formed. And so TS, we'll do this in black so that we're able to differentiate between the black line and then the blue line here. So our transition state, we've partially broken our carbon-bromine bond. And we're partially forming an alkene. Cool. And so remember that things that stabilize carbocations, specifically substitution, also stabilize alkenes. And so an alkene that is completely non-substituted, such as this one here, is not going to have a whole lot of substitution. And what that means is that the partially formed alkene is also not going to have a lot of substitution. Okay, so let's think about the transition state for the terp-butyl bromide. So the transition state, we'll do this in blue. What we've got is something that looks a little bit different. We've got a partially formed carbon-hydrogen bond, we've got a partially broken carbon-bromine bond, and then a partially formed alkene. So our base is partially pulling this off. And so what we can see is, just like the species above, we wind up having this partially formed alkene. The difference here, however, is that this partially formed alkene is a disubstituted alkene. What this means is that our alkene down here is actually more stable than our non-substituted alkene. And remember, partially formed alkenes are also stabilized by the same thing. And so, because our partially formed alkene is stabilized, our transition state to get to that point is lower. What this means is that a tertiary alkyl halide, because it's forming a more stable alkene, and therefore its transition state is more stabilized, it has to go over a smaller hump to get to the product. And remember, the size of the hump that you have to get over for the activation energy dictates how fast the reaction is. So the smaller the hump, the faster the reaction. And so in this case, this really explains why alkyl halides with greater degrees of substitution wind up having a slightly faster rate during an E2 elimination. Okay? That's all she wrote, folks. I will see you guys on Monday for your exam. Happy studying this weekend.